Hello everyone, welcome to my talk and thanks for letting me present here. I'm going to talk to you a bit about audio and music production on Plan 9. For those of you who don't know me yet, I'm Konstantinn. I'm a PhD student in bioinformatics in Heine University in Düsseldorf. And I'm also a long-time user and contributor to the 9front project. I'm also known as Quix or Quix, however you like to pronounce it. And as it happens, since a couple of years ago, I've been making some of my own music. So a lot of the motivation for this talk is to kind of explore the music and audio production side of Plan 9. How feasible is it? What is missing? And just how well does it work? So these are the topics I'm going to touch upon. Brief refresher on the audio device on Plan 9. What we can do in playback with recording, what options we have with software synthesis, what trackers are available, and what tools there are for analysis and editing. So to start with, the Plan 9 audio interface can be summarized with these 4 files: dev audio, audio CTL, audio stat, and volume. Dev audio is the most important one. That's where we can output audio or record it by either writing raw samples to the file or reading from it. The two operations are completely analogous in that sense. Audio stat is for driver-specific status, so the output is different for every driver. In this case, this is some example output for the Intel HD audio driver. It just shows how audio is routed. Audio CTL is its control counterpart, where you can send configuration messages to the driver. And finally, volume gives access to the volume, sampling rate, delay, and format controls. These can be either read or set by specific messages. So all of the drivers implement this interface, whether it's the old Realtek and Sound Blaster ones, or the newer Intel HD Audio, or the driver for the M&T Reform, the USB audio drivers, including the ones in 9front, which are in user space now. And of course, you can have more than one configured and available audio card on the system, whether it's local or has been imported through the network. There is one format that is used as a default, a bit like images, and it's the 16-bit little endian integer audio in stereo, sampled at 44.1 kilohertz, so typically corresponding to CD audio quality. And it is used as a common denominator for most applications. So most programs will try to either decode their format into this or encode from that. We have many codecs available now, some of them outside the system, such as Opus and AAC. But altogether, on 9front, we have wide coverage for pretty much all popular formats. Most of those include both a decoder and an encoder, and they also support seeking to a timestamp, which will come in, which will become significant a bit later. So the Plan 9 device, it doesn't handle mixing on its own, and it's a common use case where you might be playing some music and try to launch some other program that also wants to open dev audio. Or for instance, in games which do not implement their own mixing, they would have to open dev audio multiple times. For instance, once for sound effects and once for music. This is the case in Quake, I believe, at this point. which has one proc for sound effects and one for output and one for music, which is read either from a physical CD or from dumps on file. So the solution on 9front is MixFS, which kind of interposes itself between the client and Dev Audio by providing its own audio and volume files that are bound on top of the ones provided by Dev Audio itself, by the driver. In this way, applications don't need to care whether MixFS is present or not. The interface is strictly the same. MixFS also essentially implements a default device, since if there are multiple audio devices present on the system, MixFS can be configured to point to any one of them by default. And on top of supporting multiple writers, it also supports multiple readers for loopback. In addition, the Plan 9 audio device, it doesn't handle resampling on its own. And resampling is something that is a common task, whether it's for playing music back or for games. For instance, with Wolfenstein 3D, it stores music and sound effects in a myriad of different formats. And our port, for instance, plays back ad-lib or OPL2 sound effects and music, as well as digital sound effects, both of which are at a different format and rate, and both of them need to be resampled. So we need something that is simple and high quality enough to fit all of these use cases, and also generic. And in 9front, this is accomplished using the PCM-conf program that was later generalized into libpcm. And it can handle integer or floating point formats, different channel configurations, and so on. It has this is a snippet from the header file of the library. The interface is very, very simple. So to summarize, the primitives we have to work with are Dev Audio and Dev Volume, with a common enough sample format and rate. Audio MixFS handles mixing, and PCM-conf handles any kind of format or rate conversion. So what ends up happening is that most everything just ends up reading and writing raw samples in this same common format from a pipe or from standard in to standard out. So most tools are very small, very simple, and very composable. As a very small example, this is how an internet MP3 radio can be implemented using MixFS, leveraging the multiple readers capabilities. We would use a second MixFS here, for instance, and then simultaneously, so play is an RC script that decodes music into from any format. I'll talk about it a bit later. So it would be decoding files from a certain collection into the first MixFS. From its loopback, we can read back and encode into MP3, then write that to the second MixFS. And then we can have a listener that listens at a certain address, and that whenever a connection comes in, can essentially just read from the second MixFS's loopback and then just cat this. And clients essentially can just use aux trampoline to connect to the host and then directly decode the MP3 stream into Dev Audio. So there's some small details that are not included here. This is simplified for the presentation, but all of the significant details are here. So what do we have for playback for our music collection? Unsurprisingly, there's a lot of different approaches. In 9front, one of them is the play script, which generalizes audio decoding by kind of providing a generic file audio format detection using file. So if possible, it can read a small chunk, then run it to file, and then decide what kind of file it is, and choose the right decoder for the job. And it can use, of course, file extensions if that's not possible. But essentially, it just looks like a big switch case like this. The same way, we can get HTTP support for playing playlist files off internet radios. And we can also get MIDI support via WADFS, which exposes an instrument bank that is contained within Doom's game files. 9front ships with the shareware data for Doom 1. So if that's available, we can just mount that and use a MIDI player that is capable of using those instrument banks to get a bit nicer MIDI playback. So we can also get some very simple playback control, like pause, resume, and skipping to next track by just controlling the process. The last process in play's execution chain, which we can get from PS. This last process usually ends up being the decoder, and once it exits, then play continues on to the next track. Very similar, we can just wrap the play script to get to shuffle its arguments for shuffle play. But of course, with this approach, there's no seeking, repeat, or playlist controls. But I thought it was significant enough to showcase it because of how simple it is, since it is a very small RC script. Of course, this might not be enough, and those limitations can still be addressed, still in RC. And Umbraticus figured out several ways to do this by leveraging essentially the plumbers for controls. So we can, through a bunch of plumb rules, which I have not included here, we can add to a playlist that this program, this script manages. And all of these buttons you see here, all of this is just text, but it's plumbable. Plumbing any of these controls playback with this program. So for instance, skipping back and forth, we can shuffle, repeat, we can save the playlist here. These are even volume buttons, and just by plumbing any of these, we can switch tracks. Now, if this is not enough, we also now have Games Zook, which is a more fully featured graphical music player. It replaces Games Juke, which had similar functionality but was suffering from disuse and had several bugs. And overall, the workflow wasn't particularly convenient for some people, myself included, unfortunately. So Zook also uses playlist, which is generated by helper program mimk plist. It has a human-readable, very simple format, and it leverages lib tags for metadata extraction, including artwork, for all supported formats. The playlist itself is graphical. It can show this artwork and so on. These files don't have any, so there isn't anything to show in my example. And all of this can be controlled with buttons and also the plumber. And again, all of this has been written from scratch by Sigrid. Plumbable controls in our case also means that we can use bar to control playback in Zook and other similar programs. Bar is another program from Sigrid that looks a little bit like this, if you excuse the small screenshot. It's a program that takes over its window and maintains it on the top, meaning it's always visible. And it provides a set of buttons which you can press. Anytime you press these buttons, if you provide a script kind of like this, where here the actions, you cannot see the patterns because the runes for these multimedia symbols are missing in the font. But essentially, one button press like this will equate to a plumb command to the audio port, which Zook listens for instance, for changing tracks or toggling playback. So now a bit about software synthesis. So it's not hard to produce sound on Plan 9 with just C. There's many examples for it. There's a lot of byte beats and at this point also software pianos that have been written. When that's not enough, there are some libraries and toolkits that were ported from Unix, but they haven't seen that much use. They do work as far as I know. And of course, there's MIDI. Over the years, we've had many tools and many attempts at solving MIDI-related problems. One of them has been, MIDI playback. So for MIDI players, we have a couple. The simplest of which is Games MIDI. That's the oldest one that just samples square waves. It's very, very small. DMID was written specifically for Doom using leveraging OPL3 emulation. And SF2MID is an external MIDI player that can also use SF2 sound fonts. And there's others. So we don't really have a MIDI device, and we don't really have the tooling for editing or filtering, meaning remapping channels, for instance, or inserting events. However, interacting with USB MIDI devices, as long as they don't require specific drivers, is trivial. And I've had very good experience overall with this. And streaming MIDI over the network is also trivial. It's some have used this to just send MIDI over the network to, say, a Windows machine to control MIDI software or other hardware. So just as an example, you may have, for instance, a MIDI keyboard controller like the Akai MPC Mark II connected by USB to your computer, and then you want to send whatever events it gives you when you press the keys to a MIDI player. So DMID and OPL3 both have a streaming option where instead of decoding an entire MIDI file at once, they will interpret MIDI events in real time and produce audio that way. You can go the other way and have something like MKey, which is a very simple software piano. It can write events as you press keys to a USB endpoint, which corresponds to the input for instance, a synth. And the same can be done with a MIDI file with MID2S, which streams the contents of a file in real time. There have been several attempts at textual tools for synthesizing MIDI files, one of which is MST, which is very much unfinished and I think at this point broken, but functional enough for me to use it as a metronome, where, for instance, and this is a similar approach with many of these tools, you have commands like these, like for instance, for setting the tempo to a given BPM, initializing an instrument, and some beats. This reads this file, creates a MIDI file. It's then passed to play, which detects it as a MIDI file, and then plays it with one of the MIDI players and passes the audio to pplay, which I'll talk about later, which is just a graphical program that will loop the audio indefinitely. And there's also port of ABC tools by Umbraticus, which can be used for more sheet-like music stuff. But I don't know if it has been used a whole lot, but it does work. And again, there's no proper USB MIDI device, but it's very easy to post a file descriptor that other applications can use, like the end of a pipe. So this MIDI pipe sort of approach is something I've used for one of the trackers to be able to provide MIDI support for USB MIDI controllers that I've plugged in. Just a word also on the OPL emulators, which so far are the only hardware emulated software synthesis stuff we have. OPL2 is not included in 9front, OPL3 is. Both of them are based on the multi-arcade machine emulator, and both of them are very useful for playback of music files from games of the DOS era, which in many cases encode their music for direct playback, essentially as register value pairs coupled with a delay amount during which the sound chip is supposed to be sampled. All of them use a different sampling frequency, but the approach is exactly the same. So, for instance, for Ultima 6, there is an additional step where music files have to be decompressed, and then U6M OPL acts essentially like DMID, just sending commands to OPL2, which then synthesizes audio at this 60 hertz rate. Courtesy of Umbraticus, we also have several programs for editing instrument banks. So on the left we have OPL drums for percussion instruments. On the right, OP2 for melodic instruments in the banks. Both of these are graphical, have drop-down menus and everything you might need, as well as a preview. And again, from him, there are two trackers, one graphical and one, well, two graphical technically, and one text-based. They do work. The text-based one looks kind of like this. Just as an example to show you kind of what it might look like. This maps to operations on the chip itself, so it's a bit cryptic. And there's a lot of UTF runes missing here. Unicode, sorry. But you get the idea. One mention for Ment GUI, which is a very old program I don't know that much about, but I know it's been available since forever. It's a collection of small programs that can generate waveforms and so on and create music out of this, kind of like a modular synthesis sort of approach. And that describe their graphical user interfaces with text files. So if you look at this tool here, this oscillator tool, it can read interface that is generated by this program GUI, and the interface is very, very, the description language is very, very simple, and it allows you to create sliders, knobs, buttons, and all kinds of stuff along with, their values. And in this example, you have this oscillator piped into a tuple, which then generates audio based on the signals it gets. I haven't shown the user interface for tuple. But here is another one of the programs available in GUI, which lets you set note events. All of these are notes, and on the horizontal direction is the time, essentially. And a brief mention for Orca and 9DAW, which is porting work from Sigrid. This Orca is kind of an esoteric programming environment for creating music. It's very, very nice for live coding and stuff like this. It's very cool to look at, and also very complicated to comprehend. And then 9DAW is essentially a way to implement instruments using Faust, a functional programming language, which in a similar spirit to GUI a bit, lets you generate graphical user interfaces solely based on the code of the actual instrument. And we do have from Umbraticus also an Orca instrument named Orca OPL. Okay, a brief note on trackers now. So for those of you not familiar with trackers, if you think of sheet music as a kind of horizontal way to write music, where you write it left to right, with trackers you do it top down in a vertical layout. You have time divided into equal sized chunks or steps. Then each column in the view is divided. Each column corresponds to an instrument or sample or MIDI channel number and so on. Then all of the steps then comprise a pattern. Patterns that are chained together into songs. And each of these steps, they can trigger either a note or one or more effects. So effects are stuff like pitch bends, fade-ins, fade-outs, tremolo, vibrato, stuff like this. On 9front, we have Mod Track by Umbraticus again, which is a Amiga-style tracker written completely from scratch. It uses samples and it comes with its own sample viewer and editor. Very nifty and very quite small. Then next to this, we have two ports by Sigrid, one of ProTracker 2, so PT2 clone on Unix, and one of FastTracker 2 or FT2 clone. This is one I've used quite a bit and updated myself and made some changes to, including, for instance, using a MIDI pipe so I can play directly with a keyboard. And I've made a bunch of music using this, so it works quite well. And that's it for software trackers. And I'd just like to mention one hardware tracker, the Dirty Wave M8 or Mate. It's similar in spirit and based on Little Sound DJ or LSDJ on Game Boy. And it has an impressive set of features for a hardware tracker. It has many different sound engines, very cool ones. It can use samples, can do sample editing. It can drive MIDI hardware or be driven by it. It has built-in effects and all kinds of cool stuff like this. And under the hood is just a Teensy board. And the folks at Dirty Wave are kind enough to provide the firmware free of charge. And we have M8C now, which is a headless tracker for the headless client, for the M8, which is open source. It's in C, and it allowed many ports to devices like the Ambernic retro consoles you see on the screen, or on desktop computers and so on. What the Teensy does under the hood is it acts kind of like a USB audio card, and also provides an additional control endpoint, which is used to drive the graphical interface and to interact with the engine. And then one of the audio endpoints on the card is used to retrieve the sound that the chip actually synthesizes. So why this is relevant is because M8C has now been ported with using NOPE or NPE, the native porting environment, which was presented at a past IWP9. It only required some modifications to the USB audio driver to provide access to this special interface, the control interface for M8C. NPE itself needed a bit of work to get SDL3 and audio streams and some other missing stuff, and porting M8C itself was not particularly hard. The only bug remaining right now is reading back the audio that the chip produces. For some reason right now it's garbled, but it might be related to other problems in the USB audio port driver, sorry. But one point I wanted to make here was that the port was quite simple. Besides this one bug, even the changes required to NPE itself were pretty minimal. So that's pretty cool. Some notes on recording external equipment. So for instance, assume you have something like an electric guitar and you'd like to record from it on 9front. Right now, the options you have are either to plug it directly into your computer, like the microphone jack, and then just read from dev audio and convert to whatever, or use an USB audio card, and then the process is exactly the same, but you might get maybe higher quality. Right now, anything that is using a generic USB audio kind of interface is usually known to work. So for Behringer, for instance, there is a bunch of very simple cards that are known to work quite well. Some of their mixers, including one that I use myself, integrate the same essentially chips, so they also work on 9front as is. And devices like the Zoom H5 here, which have a USB port that can be used either to read the contents of the SD card on which everything is recorded, or to use it directly as a USB audio interface, and both work on 9front. So in practice, to give you an idea, this could be this is an example setup where you have a MIDI controller like the Akai here that sends MIDI events to this hardware sequencer here, which then drives all of these synths that are daisy-chained kind of together on and mapped to specific channels. And then all the audio that they produce is routed back to this mixer, which has an integrated audio card, and which I then just stream from directly into FLAC-Gang, for instance, to directly save the audio. Then I can do some minimal editing. And that works quite well. There aren't really any problems with latency, because most of this here is done with hardware, and the chains themselves between all the MIDI instruments are not too long. So there's no issues in practice. Just a brief note on analysis and editing. We don't have that many tools for visualizing or analyzing audio. The couple we have are, for instance, FracGraph by Umbraticus, which I use quite a lot. This just shows you a spectrogram of some audio samples passing through it. So I often have it in a pipeline just to check that there aren't any weird peaks, or that audio recording is actually working. In similar spirit, there's Pitch from Sigrid, which uses a lot of the same code just for pitch detection. And there's my own fplay, which is a bit unfinished, but instead of it being real time, it just analyzes the entire file at once and produces a plot like this. And that's it. We don't really have much else as far as analysis comes, or visualization for this kind of stuff. Then for editing, we have a bunch of small utilities, very simple ones. From Umbraticus again, we have PCM-env, which computes fade-in and fade-out envelopes, and PCM-rev, which just reverses audio. There's audio stretch, a port from Unix, which can either stretch audio without changing its pitch, or change its pitch without stretching it. And there's PCM mix, which lets us mix multiple files together and also change the overall volume. All of these use read from standard in and write the result to standard out. And I have used all of these quite extensively, both for music making, but also for guitar practice, for instance, to slow down or to tune by n semitones down or up guitar recording. Finally, for editing, there's pplay, which is something I've been working on for quite a while. It's similar in spirit to Audacity, and essentially lets you read a bunch of raw PCM audio, select ranges within it, and perform operations on them. So, for instance, you can zoom in, zoom out into ranges. You can copy, cut, and paste. You can change the contents of the range by overwriting them with the contents of a different file, or you can write them out. And there is infinite undo and redo. And more significantly, there's pipe commands, which resemble for instance, SAM. Where you can, for instance, send a given selection, a given range of data to the standard in of a given command, or replace them with the standard out of a given command, or more perhaps usefully, the caret, which lets you pipe selected range to a given command and then overwrite it with its output. So for instance, here we can use PCM mix directly to change the overall volume of this section here. So in a way, these pipeline operations kind of replace the plugin system from, say, Audacity. Finally, a word on the AWs, or digital audio workstations. We don't have anything like this on Plan 9, and I don't think it's really feasible. Many of them are very complicated projects, and many of them rely on proprietary plugins. But if it is necessary to use one alternative is to start up a VM using VMX in OpenBSD. Of OpenBSD or Linux, and then use something like Pipewire or something else to stream audio back into the host. Another alternative is to just use VNC or remote desktop or whatever, and connect to a Linux or Windows or whatever machine that is running one of these DAWs. And of course, I would be eternally grateful if someone re-implements the Dalai Lama. But yeah, that's all I have as far as the rundown. Just to conclude, I think 9front has significantly expanded the audio capabilities of a Plan 9 system over the many years it has existed. A lot of work has been put into all the tooling and hardware support. and the interfaces are all the same. Everything has been kept the way it should be. The tools are fairly small, fairly minimal, and fairly, effective. And what might be in future 9-front DAW is maybe what we already have. That is a collection of tools and scripts that do specific purposes, that accomplish specific purposes. Much like what I've been doing in my own music production. And I dare say it works. I'm not the only one who has made music on 9-front over the years. And with that, thank you. And I'll be happy to take any questions. So your question is about real time and like latency and how well it performs under load. Well, now I'm hearing myself. In my experience, I haven't had much issues when it comes to recording. Very often we set priority for the audio process when we do in several applications. That's the case in pplay, and it's the case in, I think, MixFS, maybe a couple of other programs, and it works well enough. It really depends on what you mean by high load. For my purposes, as far as producing music, I don't do most of my processing in software. Most of it is in hardware, so I don't get much load in my use case, if that makes sense. So, to repeat the question, you're asking if it would be any different if we had, say, like a web server that had to, serve a bunch of audio in real time to many different clients. I mean, it depends on how many. If it's 2,000 or like 200,000, of course, in the latter case, it might be a bit difficult. But for realistic, I guess, workloads for a Plan 9 system, so far I haven't really seen any issues. I think it would fare fine in most cases. I mean, this isn't, unless it's something like Opus or it's something specific where like decoding the audio or encoding it or something, unless this is high load in itself, I don't think it would put that much pressure, even if you had that many concurrent connections. Thank you. So do you mean what would it take to support this kind of hardware, or what would it take to re-implement some of the functionality in, say, Ableton? So the question is, I'll generalize a bit, but what does it take to add support for an audio peripheral that doesn't use, say, like a generic USB driver or something like this? I don't know, to be honest. There are some devices that use more annoying proprietary interfaces than others. For instance, I have a Yamaha mixer, which has an integrated audio card, but it doesn't work on anything I have. So whether that's 9-front or Windows XP or like whatever, it just does not work. Others require just light modification, like for instance, the Dirty Wave Mate. That is essentially still a generic audio card, even if it has some, additional knobs and stuff. And so I don't know. It really depends on the kind of hardware. Yeah, I don't think I can predict in advance. Yep. And if you need any help, of course, feel free. Okay, so your question is essentially like, how can we use the tools we have to do something like a DJ setup where you insert transitions between songs, you match tempos between tracks, this kind of stuff. The answer is that we do not have that. We do not really have tools to do stuff easily, like crossfades or to analyze and match tempos. We don't have yet stuff to, for instance, slice tempos by beat or whatever. Slice samples, sorry. So this kind of stuff is missing. Yeah, what we can do is implement simple radios like this and serve them to clients, but we cannot do this sort of editing yet. Thank you very much.